Okay.
So the last time we had started with, well, before last time we started with thermal physics. Talking about the kinetic particle model of matter. We talked about solids having a definite shape and volume. Liquids have a definite shape, but they take, definite volume, but they take the shape of the container. Why is that? Because the particles are further apart because they have more energy as compared to solids. Gases do not have definite shape, nor do they have a definite volume. It depends on the container they're in. They are very much far apart and they have much more energy. Right? Uh, right now, the energy of the particles and the attractive and repulsive forces between neighboring particles affect their shape and volume. So we talked about that. Then we talked about, right, the relationship between temperature and kinetic energy. So the more the temperature, the more the vibration the molecules, the more average kinetic energy they have, and vice versa. If temperature is reduced, lesser vibrations, lesser overall average kinetic energy. Then we talked about the Kelvin scale. So there is a temperature called absolute zero,
By
where
the way, so your screen is not being shared.
oh god, I tend to do that very often. You told me earlier. Can you see that?
Yeah.
Okay. So the temperature at which particles lose all of their kinetic energy is called absolute zero, and that is minus 273 degrees centigrade or 0 degrees Kelvin. Right, and so the relationship between that, right, 0 degrees centigrade is 273 degrees Kelvin. Uh, we talked about the Kelvin scale being represented by the symbol T, degrees centigrade being represented by the symbol theta, and then this particular formula for converting Kelvin to centigrade, well, actually converting centigrade to Kelvin and vice versa. We did, a few questions. We also looked at the graph explaining, right, why we have this value of absolute zero. Then we talked about pressure and kinetic energy, right? So increasing the temperature increases kinetic energy, which increases the pressure because it increases the frequency of collisions, which increases the force the particles are exerting. This obviously you're talking about gases. We talked about Brownian motion, which is the movement of fine particles in air, the random movement of fine particles in air due to collision with air molecules of the air. Then we started talking about the relationship between temperature, pressure, and volume of gases. And the first thing we covered is atmospheric pressure and the fact that there is a significant pressure being exerted by the air. It has a weight of about 500 newtons, and which comes up to 100 kilopascals or 100,000 pascals. And the pressure of the air was demonstrated if a can is emptied of air, if there's vacuum in a can or a container, a compressible container, obviously, then it will collapse due to atmospheric pressure. I shared a video regarding that as well, and that is where we left off. I'm assuming there are no questions up till this point.
No.
Haram?
No.
Okay. All right. So we've kind of talked about the effect on pressure of a change in temperature. But let's go over that. Take a new page. I already had a new page. So, in fact, you know what? Eat this one. Okay. So we're going to talk about effect on pressure of a change in temperature while keeping a constant volume. So when we heat a gas, right, obviously temperature is going to rise. Which is going to increase the average speed of the particles, the average kinetic energy of the particles. Okay. Right now, if the volume is of the container is fixed, right? And what do they mean by the volume of the container being fixed? It means that you don't have something like a balloon that's going to expand. Okay, because if the size of the container is expandable, then the volume will change, right? And so you don't have that. The volume is fixed, so the volume is not
So
changing.
it doesn't increase and it doesn't decrease either, right?
The volume is fixed, right? Whatever volume you have, that's it,
Okay.
right? And so what you will notice is that the pressure of the gas will increase. And why will it increase? For reasons that you already covered, right? Because right, they are more frequent and more uh, violent collisions of the gas particles. More frequent collisions of gas particles with walls of container, right, with more force. So the more violent collisions with more force. That's something we already covered. Now, let's talk about effect on pressure of a change in volume.
Can you please elaborate it,
Elaborate what?
what you were explaining?
This part?
Yeah.
Just a sec. We got constant temperature. I put in the heading. I don't know if I need more space. Uh, okay. Let's use this space. You have, let's say, a container made of steel, for example, right? And you've got gas particles in it. And what you do is you provide energy to it in the form of heat. And so that increases the temperature. Now, before providing heat, obviously, the particles are moving randomly, right? And they have certain energy. So when you're providing heat and the temperature is increasing, they will move faster, right? And they will have more energy. And we know that energy is related to force, right? So the more energy they have, right, the stronger the collision will be with the walls of the container, right? And by stronger, we mean that the collisions will have more force to them. Following?
Yeah.
Karan?
Yeah.
Okay. Now, how does that affect, how does that increase pressure, right? Because pressure is force upon area. So when force is going up and the area is the same, right? How much area there is, right? The size of the particle, right? It's hitting the container at this point. So the area is the same, but it's hitting with greater force. That means the pressure is also going up. Does that make sense?
Okay. Yeah.
Alright?
Yeah.
Make sense? Clear?
Yes.
Okay. Now, effect on pressure of a change in volume with constant temperature. Now, this time you're not changing the temperature, keeping the temperature constant. What you're doing is you have a container, right? And this thing is filled with gas, right? Obviously, this whole thing is like volume 1. And obviously, the gas particles are spread throughout this container. What you're doing is that you are, in this case, decreasing the volume. So let me just make this black so it stands out. Okay. Now you've decreased the volume, right? So you still have the same gas, right? And the same number of particles of the gas in less space, right? You've got volume 2, and volume 2 is less than volume 1. You understand the symbol, right?
Yeah.
Yes, no?
Yeah.
Aram?
Yes.
Okay. So volume 2 is less than volume 1. What's happening is, right, the energy of the particles has not increased, right? But now you have, right, energy of the particles, average energy is the same, but you have more particles in less space, and therefore there are more collisions, right, happening with the surface of the container in that less space. And right, so what's happening is Right, now the area in this case, should I say it's less? Basically what's happening is you have twice as many collisions happening per second. Right, and this is in case, right, if you've halved the volume. Doesn't seem like it's half, but let's assume it's half. Right, so you have half the volume. And so you've got twice as many collisions happening or occurring per second as compared to volume 1. And that will, you know, cause the pressure to increase. Does that make sense?
Yeah.
Yes.
Yes? Okay. In fact, right, what actually happens is causes the pressure doubles. And so with that, we will, right, move into talking about the, right, relationships between pressure and volume basically. The, right, the other gas laws. So there are 3 gas laws. You have Boyle's law, and you can judge by the spelling that it's someone's name. You have Charles' law.
That is also sounds name, right?
Charles's law, and then you've got the pressure law. Right, now as far as your syllabus is concerned, the only one you need to know is Boyle's law. Charles's law and pressure law are given in your texts, but they are not part of, you know, O level or IGCSE. Okay, but for
Okay.
some reason, they've included the practical for Charles's law in O level, even though the, right, law itself is not part of the syllabus. Anyway, so let's talk about Boyle's law. Right, after that, I will go over the practicals. So, right, the relationship between the pressure of a gas and its volume, which we just talked about. Right, so it talks about the variation or the change in gas pressure with volume. Right, and so what happens is, right, based on one of the practical experiments that are performed, and they're in your book, so we'll take a look at it after this. Right, what they do is that they plot a graph of volume versus pressure. And what they notice is that as the volume increases, pressure decreases. Right? And so for any given volume and pressure, that isn't accurate. Oops, what just happened? Okay, that's good. So, right, you take the pressure at any volume. We are just in a straight line, trying to be, and then you take half of that volume. So we're somewhere over here, I guess. Now this isn't very accurate, right? But if you take half of that volume, what you'll notice is that the pressure over here doubles. And so what we understand from this is that pressure and volume are inversely proportional. So, right, pressure is inversely proportional to volume. Or you could say, right, pressure equals to a constant times 1 over volume. Or you could say that PV equals to constant. Are you following so far?
Yeah.
Okay. Now, if, right, and this should be a capital V, sorry, that's it, capital V. Now, if the, the multiple of pressure and volume is constant, and so taking a set of readings, what you should get is P1 V1 should equal to P2 V2, which should all equal to a constant, and that constant would be the same.
Yeah.
Does that make sense? Are you following?
Yeah.
Yeah.
Right? And that is basically, this is Boyle's law. Right? P1 V1 equals to P2 V2. So what this helps us to understand is for a particular gas, right, at a particular pressure having a particular volume, right? So you get a constant, fine. If, for example, you change either one of these, you change the pressure of the gas or you change the volume of the gas in like, right, a new situation. And so you can figure out, okay, if the pressure changed, what is the new volume? Or if the volume changed, what is the new pressure of that gas? That's what Boyle's law helps, right? So it can be put into words. the right Boyle's law that the pressure of a fixed mass of gas is inversely proportional to its volume if its temperature is kept constant. Right, so that's Boyle's law in words. This is the equation for Boyle's law. And let's put that into a bit of practice. So there is right a question, a work example, or in fact right, let's do something else, right? So there's a question, you have a fixed mass of gas with a volume. We're doing the question, right? The volume of a fixed mass of gas is 9 centimeter cube, and the pressure is 1 into 10 to the power 5 pascals. So basically atmospheric pressure. So what will the volume be when the pressure will be changed to 3 into 10 to the power 5 pascals? And so, right, we have P1, P1 equals to P2, so you got 9 millimeter cube multiplied by 1 into the power 5 pascals equals to, right, 3 into 10 to the power 5 pascals multiplied by x centimeter cube. So x will equal to 9 into 1 into 10 to the power 5 divided by 3 into 10 to the power 5. So you're going to get rid of the powers, you're going to and so you're going to get 3 centimeter cube, which is the volume. Did you follow along?
Yeah.
Aram?
Yeah.
Simple?
Yes. Yeah.
Right, so pascals and centimeter cubes, all of that might seem a bit overwhelming, but it's just basic math and knowing how to move things about. All right.
Pascal is the unit of pressure. Pascal represents pressure. Pascal represents pressure. No?
Pascals represents pressure. Yes.
Okay.
Achha, one thing they mention in the text that since pressure is inversely proportional to volume, that would mean that pressure is directly proportional to 1 over 1, because that's basically what this is, right? This thing. Right, that's what they're talking about. And so when you plot pressure against volume, you see that change, right? That reducing the pressure, reducing the volume increases the pressure, and vice versa. Reducing the pressure increases the volume. But if you plot a graph of 1 over volume versus pressure, you get a straight line. And so this is a linear relationship. Okay.
Yeah.
Yeah.
Okay. Now, as far as the content that needs to be explained is concerned on the whiteboard, right? That's all for today. Now I will take you to the text where we will talk about, we will cover, not talk about, but cover the practicals that are given right as part of the chapter. From the Google Meet allows that. There we are. All right, so this is the O level text. All right, so nothing here, nothing here, nothing here. And then for the O level, the experiment for Brownian motion is part of going further, so it's not part of your syllabus. For the IGCSE, however, it is part of the syllabus. So let's just take a look at that. And so what they're doing is testing Brownian motion, and right, you can look at the setup. There's a microscope, right? There is this container. There's a light source, a lamp. There's a glass rod that will act as a lens, right? You've got some smoke over here, right? And there's a lid covering it so the smoke stays within this container, right? There's a window, so this part of the lid is glass so that you're able to observe. So what you're doing is carefully adjust the microscope until you see bright specks dancing around haphazardly. The specks are smoke particles seen by reflected light. So this light is falling on the smoke particles, which appear as bright specks. Or for example, you've seen dust in your room in sunlight, right? That's basically what you're seeing. The random motion is called Brownian motion and is evidence for the kinetic particle model of matter. This motion is due to collisions between the microscopic particles in a suspension and the particles of a gas or liquid. So basically the smoke particles and the air particles colliding, right, as we've gone over already. So the apparatus is shown in the figure. First fill the glass cell with smoke using a match. Replace the lid on the apparatus and set it on the microscope platform. Connect a lamp to a 12-volt supply. The glass rod acts as a lens and focuses light in the smoke. So we've understood that. This is the kind of motion. Of course, you won't see squiggly lines. You'll just see the particles moving around randomly. Okay. So that is the practical for Brownian motion. Next is a practical for the effect on pressure of temperature. So increasing or decreasing temperature and how that has an effect on pressure. So it's part of both the O level and the IGCSE. So, right, this is the setup that's required. We're giving you some safety. The Borden gauge should be firmly clamped to prevent toppling. So this thing, right, should be secured so it doesn't fall over. You need eye protection, and you need to take care with the hot apparatus because you are heating water, and so you need to be careful. All right, so the apparatus is shown in figure 2.1.9. The rubber tubing from the flask to the pressure gauge should be as short as possible. All right, so there's air inside this flask. Right, you tap the flask with a rubber bung. That's what it's called. There's a pipe coming out, and that's attached to this tubing that is going into the pressure gauge. It should be as short as possible. Why should it be short as possible? So that, right, the air does not lose heat while moving to the pressure gauge, If it loses heat, right, it loses energy. If it loses energy, there's less force in the collisions of the particles. If there's less force in the collision of the particles, there's less pressure. So even though the gas, the air would be under high pressure coming out of the flask if the tubing is long, even if slightly, it would affect the pressure reading in the gauge. The flask must be in water almost to the top of its neck and be securely clamped to keep it off the bottom of the can. Why do we want to do these two things? Right, we want it in water. Why do you want it in water? You are heating water. Water gets heated. It's all the way up till the neck, right, just below the rubber bung, as you can see. And so the water gets uniformly heated, and so the flask gets uniformly heated from all sides, right? And so there's uniform heating of all the gas, the air in the flask. It is kept above, so there's, right, it's not directly being heated, and so the gas at the bottom of the flask, if it were near the heat source, it would heat up very quickly and move into the pressure gauge, whereas the rest might take time to warm up, right, because it's farther from the heat source. And so you're warming up the whole thing, right, up till the neck, so it's not as if the gas is being heated only at the bottom of the flask, and as it moves up, it's cooling. It's not cooling, right? So you're maintaining your apparatus, the conditions of your apparatus. An experiment. Heat can be supplied to the water by standing the can on a hot water plate or a tripod over a Bunsen burner, so, right, whichever works. Record the pressure over a wide range of temperatures. So you start off with lower temperatures, you heat it up, you got a thermometer to check what temperature you're at, record the readings of the pressure gauge. But before taking a reading from the thermometer, stop heating. So here's something to, have good results. So you've heated it, it's gone up till a certain temperature, stop heating, stir the water, allow time for the gauge reading to become steady. Why are you doing this? You are stopping providing heat, so it doesn't keep getting hotter, and so that heat is not being constantly transferred, right? You're stirring so that the water, maybe it's hotter at the bottom, it's a bit cooler comparatively at the top, and so the heating is uniformly distributed in the water, and so that heating is then uniformly transferred to the gas in the flask, right? And then give some time for this reading to become constant. Why? Because fluctuations in temperature will cause fluctuations in the reading, and so when the temperature becomes constant, the reading will become constant, and so that constant reading is the actual reading that you're looking for.
Okay.
The air in the flask will then be at the temperature of the water, as I just explained. Take about 6 readings and tabulate the results. Plot a graph of pressure on the y-axis and temperature on the x-axis. Any questions?
No.
Aram?
No.
Are you sure? It's all good?
Yeah.
Okay. So that was the setup for effect of temperature on pressure while keeping the volume constant. Right. Next up, you have effect of volume on pressure while keeping the temperature constant. Right. So you're increase or decreasing the volume of the gas, and so you're checking how that would affect the pressure of the gas. You're keeping the temperature constant. The temperature is not changing. So the setup is different. The setup is given on the next page. We'll get to that. Changes in the volume of gas due to pressure changes can be studied using the apparatus in figure 2.1.10. So this is it. Right. Again, you've got a Bourdon gauge for the pressure. Right. You've got this glass tube with air inside it, and you've got oil. So you're pumping oil, right, into the tube. So what you're doing, right, the volume V of air trapped in the glass tube is read off on the scale behind, right? So, right, this is the volume. So when, right, the lower the oil, the more the volume, obviously, And so perhaps in this particular one, it's at, you read the lower meniscus. So I can zoom in further. This is a nice high quality image. And so it's, I believe, at 36. Why is it 36? We're starting from 0 at the top. So the numbers are actually increasing while you're going down. And when you are reading scales, you need to, make sure which way the readings are going. So the readings are increasing as you come down. So you've got 30, 35, and then I believe that this should be 36. Right? Or perhaps a little even less than 36, maybe 35.5. Anyway, that's not the point, but just to read it. The pressure is altered by pumping air from a foot pump into the space above the oil reservoir. So as I was saying, the pressure is altered by pumping air from a foot pump into the space above the oil reservoir. This forces more oil into the glass tube and increases the pressure P on the air in it. So you're using this pump to force, well, actually, right, not this pump, but that's the connection, right? This tubing that's going to a foot pump, you're pressing on the foot pump, right? It's, well, what's happening is it's pumping air into this, right, which is forcing oil into the glass tube. And as the oil rises, there's more oil in here, right? The volume of the gas is the same, right? I mean, technically not the volume. The mass of the gas is same. So you've got the same mass of gas, but the space it has is becoming lesser, right? So the volume is decreasing. Right, so it's forcing more oil into the glass tube and increases the pressure P on the air. P is measured, right? Take about 6 different measurements, plot a graph of pressure versus volume. So the pressure is decreasing, the volume should increase. Wait, what did I say? The volume is decreasing, the pressure should increase. I believe I said it the other way around.
Yeah.
So the volume is decreasing, the pressure should increase. That is what we would notice, right? According to this. And so as the graph I tried to make, this is much better made, obviously, so you can clearly see as volume decreases, pressure increases, right? If you plot the inverse, you get a linear relationship. Right? So that is for pressure and temperature and pressure and volume. And then there's this experiment which is given in O Level for some reason, which is a relationship between it's Charges' law, so it is a relationship between volume and temperature, and that means that as the temperature increases, the volume will increase, as the temperature decreases, the volume will decrease. I'm actually going to skip this for the time being because I don't get why they've included the practical when the concept itself is not part of the syllabus, as you can see. And so we're done for the day. Next class we're going to move on to the next chapter. Push forward. We're going to talk about thermal properties and temperature. Any questions?
No. No.
Oh, that's good, Alex. So I'll see you next class.
Inshallah.
Allah.
Last.